So now let's take a look at what we saw in this lab and how can we apply that to the real world. So let's talk about the final results. I need you to copy this data down into your notebook. In your chart, this is what really happened. The sand and the water both started at 71.2 degrees, and when the lamp was on for 10 minutes, it gave each sample energy, their particles moved faster, and hence their temperature went up. Now you'll notice the sand went up to 79.6, which means it went up 8.4 degrees. The water went up to 74.3, which means it only went up 3.1 degrees. Which, if you think about it, this is kind of odd because they were sitting underneath the same lamp. They were getting the same amount of energy, and they both started off at the same temperature, but yet the sand got a lot hotter than the water. Okay, but the data is what the data is. And we're going to take this, and this is correct numbers. We are going to take these numbers and we're going to apply them to what this means out there in the real world. But remember, we didn't just heat them up, we let them cool down. And here's the cooling down numbers. The sand was 79.6 because that's what it was when we turned the lamp off. And we let it sit for 10 minutes and we see that it went down to 72.5, which means it was a change of 7.1 degrees. On the other hand, the water, 74.3, went down to 72.5. The water only cooled down 1.8. So wait a minute. So when the lamp was on, the sand changed a lot more than the water. The sand got hotter. But when the lamp was turned off, the sand also got cooler. It cooled down more than the water. So our conclusion would be something like this, that water doesn't heat up and cool down as much as sand. And in this activity, this is meant to model the Earth. Well, you know where the water is in the Earth. It's pretty much in the oceans. And the sand is going to represent the land on our planet. So what does this mean? That means, well, think about our planet. We've got water in the oceans, and we've got sand, like at the beach. And if you've ever been to the beach in the summertime and you walk across the sand, you know it is generally pretty hot. It'll burn your feet. But yet you run down here and you jump in the water and the water feels nice and cool. But they're both sitting under the same sun. They're both getting the same amount of energy, yet the sand in the beach ends up being a lot hotter than the water in the ocean. So there's something different going on here. And I also want to pose this to you. Think about going and walking on the beach at night. If you've ever walked on the beach at night, especially long after sunset, the sand generally feels cool on your feet. It doesn't feel hot anymore. Well, that means the sand cools down a lot because it was hot during the day and it's cool at night. And that's very similar to what we saw in our lab when we turned the light on and we turned the light off. The sand got hot real easy, but it also cooled down pretty easy. So you can see how this is applicable to situations out there in the real world. Well, this situation, this idea, this concept has a fancy name to it, and it's called specific heat. Specific heat is the amount of energy it takes to, and I'm going to change this. I'm not going to say raise. The more correct term is change. Specific heat is the amount of energy it takes to change a material's temperature. Whether you're making it hotter or you're making it colder, you have to change the amount of energy. And the amount of energy it takes to change something's temperature is called its specific heat. So why do things heat up differently? Why does the water and the sand sitting under the same sun end up a different temperature? Well, think about it this way. Think about moving a shot put versus a beach ball. Which one takes more energy to move? Well, it's certainly going to be the shot put. This thing over here is heavy, so it takes a lot of energy to get that thing moving. That's kind of like water. Water takes a lot of energy to get its stuff moving. And remember, you got to get moving to cause the friction, which is what temperature is. So the sand is like the beach ball. Beach ball is easy to get moving. It doesn't take much effort at all to get the beach ball moving, and that's why sand gets so hot under the sun, because it's easy to get sand particles moving and causing the friction, which will cause the temperature to go up. This is the concept of specific heat. Now, each substance has a specific heat. That's why it says it's specific. It's a set amount of energy it takes to make that particular material change temperature. Water has a high specific heat, and you know this. If you've ever put some water in a pot and put it on the stove, like you're going to cook some pasta, you know, man, it takes a long time. That water's got to sit on the stove for a long time until it gets hot enough to cook the pasta, because it takes a lot of energy to make water hot. On the other hand, the ground, which is like our sand in this experiment, or the air, have very low specific heats. They get hot pretty easy. And I can kind of prove that to you about the air anyway. If you've ever been outside on a cool morning, just think like in the wintertime, as soon as the sun comes up, you can almost feel the temperature change, because the air will get hot very, very easily. So as soon as the sun comes up, the air gets the energy and it starts to get hot. It's also true the other way around. Sometimes in the wintertime, especially, as soon as the sun goes down, you can feel it getting colder, because air changes temperature very easily. It doesn't take much energy to cause that change to happen. That's its specific heat. Now let's talk about the applications. I'm going to go over some applications for you and with you, and we're going to talk about how does this, what we saw in this lab, impact the real world.
Back there behind me is the Pacific Ocean. Now, the Pacific Ocean is very, very large. It's very, very deep. It has a lot of water in it. And we know that water doesn't change temperatures very easily. It's very slow to heat up, and it is slow to cool down. So places that are near water do the same. If you're along the coast, you don't get as hot or as cold as other places that are away from the water. Well, I went down there this morning and I took the temperature. It's July 25th, and the temperature of that ocean is 53 degrees. That's not very warm. Even though the sun has been shining all summer, there's too much water out there for it to ever get really, really warm. That means that this town back there in the fog, Fort Bragg, California, is never going to get really hot, even in the end of summer. The high temperature while I've been here this week has been about 60, 65 degrees. Even though it's land, and land can heat up fairly easily, it's too close to this water, which stays cool. So that means the land up and down the California coast stays fairly cool in the summertime, because that water never gets really hot. On the flip side, in the wintertime, that water doesn't change too much. It won't get pretty much below 50 degrees. So that means the places along the coast in California also don't get exceptionally cold in the wintertime. And this is very much true in places up and down the Pacific coast, where the Pacific Ocean's temperature stays pretty much the same year round. So the temperatures up and down the California, Oregon, and Washington coast don't change much from summer to winter.
Now, islands like Hawaii really don't change temperature that much, because look at Hawaii. It is surrounded by a bunch of water. There's very little land and lots of water. Well, water doesn't heat up and cool down very easily. That means Hawaii doesn't heat up and cool down very easily, which means it never gets really hot and it never gets really cold in the state of Hawaii.
So here I am at the airport in Honolulu, Hawaii. Hawaii, being an island surrounded by water close to the equator, means that the temperatures here don't change that much. Never really gets that hot, never really gets that cold. And one real good example of how constant the temperature is how they design the airport. You notice here behind me, there are no windows. A good portion of the airport in Honolulu is just open to the outside. because it never really gets hot and it never really gets cold, so you don't really need an air conditioner or a heater. So a lot of your buildings, like your hotels and your airports and such, are just left to the open air because the temperature really never gets that hot or that cold, and it's because it is surrounded by water and close to the equator.
Take another island. It's Jamaica, which is an island in the Caribbean. It's an island. It's surrounded by water. The water doesn't change temperature that much. That means the temperatures in Jamaica remain pretty constant. This picture down here is the lobby of the hotel I stayed at. Big fancy hotel resort, and you'll notice there's no doors, there's no windows, because they don't need air conditioning. They don't need a heater because it never gets really, really hot, and it also doesn't get really, really cold because they're surrounded by the water. A lot of the restaurants on the property were like this. They were just open air. They were outside. And it was okay because it wasn't really that hot. And in the wintertime, it didn't really get that cold because it's an island surrounded by water, and water just doesn't change temperatures that easily. Now, the same is also true with other places that have a large amount of water, like a rainforest or a swamp, wetland. Places that have a lot of swampy ground, well, there's a lot of water there, and water doesn't heat up or cool down very easily. So swampy areas are going to have temperatures that remain a little bit more constant than dry areas. A rainforest. Rainforest is an extreme case of that because it's a rainforest. There's lots of water there. It rains a lot. Very, very wet, damp. So all of that water is not going to get really, really hot. It's also not going to get really, really cold. So a rainforest tends to have pretty constant temperatures. And this is true any place that has a lot of water in the environment is going to stay remarkably constant with its temperatures. It's not going to change a lot. And that's what we saw in this lab. Now, on the other side, let's take Lincoln, Nebraska, right here in the middle of our country. Lincoln is about as far away from any ocean as you can get in our country. You can even see the Arctic Ocean off the top. So Lincoln is surrounded by a bunch of sand, a bunch of land. Think about the sand in our lab. That's all Lincoln has got all around it for thousands of miles in either direction. Well, we saw that sand heats up and cools down very easily. So let's look at Lincoln. Lincoln's temperature in July is about 88 degrees. That's the average. That's pretty hot. That's very comparable to what we have here in Georgia. But let's look at Lincoln in January. Its average high temperature is only 32. It's freezing, literally. Well, because Lincoln is so far away from the water, it can get really hot in the summer and then turn around and get really cold in the winter, as opposed to a place like Hawaii that's going to be the same in summer and winter because it's surrounded by water. Lincoln has the opposite going for it, and that is because it is so far away from water, its temperatures are going to change a lot throughout the year. This is also true of deserts. Think about deserts. Deserts are dry. There's no water at all. Well, where there's no water, you can get really hot. And that's one of the reasons why deserts get so hot is because it's a desert. There's no water. And where it's that dry, you can get really hot very easily. This is Death Valley National Park in Southern California, one of the hottest places in the world. And one of the reasons why it gets so hot is because it's away from the ocean, and it is so super dry that when the sun comes out, it can get exceptionally hot. Well, how hot? I think this was 2018 when I was there, it was 121 degrees. This is the thermometer right outside the visitor center. And surprisingly enough, this actually isn't the hottest that I've ever experienced in Death Valley. When I was there in 1999, it was actually 122 degrees. And just recently, in August of this year, the temperature there hit 130 degrees. It's one of the highest temperatures recorded. Death Valley is one of the hottest places on the planet, and one of the reasons why it gets so high is because there's no water. Where you don't have water, your temperatures can get hot very easily, as you see there in Death Valley. Most of you guys know that I'm the cross-country coach here at Centennial, so I'm a lifelong runner. One thing fun and interesting and neat that I did on this particular day was I went for a run at 121 degrees just to say that I did it. Okay, so let's summarize our applications. We're going to make this list there at the bottom of the lab sheet. Locations near the ocean do not change temperature easily. Oh, do no? We need a T in there. Do not change temperature easily. Think islands and places on the coast. Wet places like swamps and rainforests do not change temperature easily. The flip side of that, places far away from the water can get hot and get cold. They can change their temperatures easily, just like the sand in our lab today. Also, dry places without any water can get very hot and very cold. Their temperatures can change very easily. So we need to copy these applications into the notebook. Pause the video, get these in there, and then come back for the closing. In closing, after you've completed this presentation, go back to the meeting and in the chat, prove to me that you learned something today. Prove to me that you were listening and you paid attention. And you can do this a couple of ways. One, you can ask me a question. And this can be about anything even closely related to something I said, a picture I showed you. This could be, I wonder, well, if this is this, why is that? It can be any question that even remotely connects to what was presented. Or you can also tell me an interesting fact. You can make a comment. Say, hey, coach, I really thought that was neat that this, or I can't believe that, or, oh, yeah, my family went on a vacation to Death Valley in 2007 when I was 4 years old. I don't remember, whatever. Prove to me that you watched this presentation and that you learned something from doing so. So you type that in the chat when you're finished.